compounds which can identify bandit structure in MDPs.
Great. Thank you for the introduction, and thank you for coming to this talk. We are going to talk about reinforcement learning solutions which are able to identify the appropriate learning framework. What do we mean by learning framework, first of all? Well, there are, for example, MDPs, MDPs, and bandits. And we would like to understand what is the appropriate framework to use. Let's start with an example. Consider the online advertising. For example, there is a user that is browsing Amazon pages, and your objective is to provide some recommendation to the user, and you would like to make sure you recommend the best item according to the history that you are seeing, that the user is generating. And you would like to maximize maybe the click probability on this item because you want to sell it, or maybe you would like to maximize the profit. Either way, this is a one-step decision, and the problem is best framed as a bandit problem. But maybe you want to capture some higher order give So for example, you might want to recommend the best product that will not only give you the highest immediate click probability, but will also maximize the number of purchases over the whole session. And this is best framed as MDP or even a POMDP problem if you do not know in what state the user is. I guess the first question you might ask is, can we use deep learning? And maybe, the answer is maybe. In this work, rather, we focus on obtaining something that is provable, an algorithm that can move from macro decision processes to bandit if the underlying process is really a bandit problem. And of course, this would like to address the issue of choosing between different frameworks, one that has more representational power and one that is more statistically efficient but maybe less expressive. I guess the first question is this even possible? Can we identify the learning framework? We have POMDPs, MDPs, and bandits. They are subset. Bandits is a subset of MDPs. And we are going to focus on the problem of exploration. In exploration, the world is unknown. You're trying to construct a model of the world, and you're trying to figure out what's the optimal policy. But you're also being tested as you are learning. So it is not a pure exploration problem where you build a model of the system and then you return a policy. You're really compelled to exploit the knowledge that you have, but at the same time you have to explore to improve your knowledge about the system. And the typical way in which the agent's performance is assessed is by looking at the regret, which is the difference between the maximum expected cumulative reward by following the optimal policy and the one generated by the policy that the agent is taking. So for tabular contextual bandits, for example, it's very well understood that we have upper bounds and we have lower bounds, and those are essentially matching up to lower order logarithmic terms and maybe constants. For macro decision processes, last year there was an interesting paper that was achieving in the leading order term the lower bound that was previously established for episodic macro decision processes. And I think what's important here is SNA are the number of states in action, and they have the number of parameters in the system. You can reduce that by doing maybe value function approximation. And what really distinguishes the regret on MDPs to the regret on bandits is this extra H that we have that is representative of the time horizon. And what we would like to do, if we are to design an algorithm that can switch from both, we have to find a way to remove the H so that we achieve the regret typical of bandit problems. What is the change in the learning framework that we consider? Well, as I said, there are results for tabular environments. They talk about bandits and MDPs, and we have a thorough understanding of these two settings, in these two tabular settings, at least for episodic MDP, we have matching upper and lower bounds. Of course, a more interesting problem is that of function approximation. The way in which people typically use bandits, I think, is by doing some sort of function approximation. And of course, people are trying to do that for Markov decision processes as well. Deep learning is something that is receiving a lot of attention, but unfortunately, it doesn't really come with guarantees yet. Here I am specifically talking about the problem of exploration. There is off-policy learning for which we have some results. Here we are really trying to interact with the environment and trying to get information out of the environment in an online fashion, and we are being assessed while we do this. And unfortunately, there are not really many results for exploration with value function approximation, not even in the simple linear setting. So by necessity, we have to consider the tabular case, and we consider switching between MDPs to contextual bandits, both in the episodic case, MDPs, and in the infinite horizon undiscounted case. The idea is basically the same. To describe the problem, we have to introduce what we call the bandit MDP, which is essentially an MDP which is in fact generated by a bandit problem. The agent is going to see some states, is going to be in some states, is going to take actions, is going to get rewards out of the system, and it is going to experience transition to some next state. But in reality, it doesn't know that the next state is really generated by an underlying generative model that does not take into account the state in which the agent is currently in and the action it has taken. It's a bandit problem. So the successor state is always sampled from an underlying distribution that is fixed, and the agent is not able to control this distribution or to influence it. Of course, it doesn't know that. So the agent, what it sees is still an MDP. It is expecting delayed consequences, and it is trying to optimize for a policy for the full edge state horizon problem. So you might be thinking, what if I take this action and maybe I trade in some instantaneous reward, and maybe this allows me to get to a better state, and from there I can enjoy better rewards. It basically doesn't know. It cannot influence the system dynamics. And the paradigm that we are going to use is that of optimism in the face of uncertainty, which is basically, I guess, the predominant way to do exploration. We maintain empirical estimates, and we give some exploration bonus, and we use that to construct an optimistic value function. And of course, you would like to choose the smallest exploration bonus afforded by the problem, because you don't really want to over-explore. For example, if you have a deterministic MDP, really there's no need for much exploration. You can just test every state and action once, and then you know how the model works. Of course, the situation is more tricky if you do not know the MDP is deterministic. So it is, you need to construct some exploration bonus, which in a certain sense is as tight as possible, and it barely compensates the statistical error that may arise due to randomness. So how do we construct this exploration bonus? Well, the typical way to do that is to, as I said, to take some maximum likelihood estimate, for example, of the Q star values, and try to construct an optimistic policy or an optimistic Q value by adding some exploration term. For those of you that are familiar with the bandit analysis, you will recognize that this is very similar to what, for example, upper confidence bound by Peter Auer is doing, only that they have a slightly different choice of the exploration bonus. Essentially, for a bandit problem, they put 1 divided by square root of n times some logarithmic factors. The idea is that rewards are assumed to be bounded between 0 and 1. So really the maximum mistake that you can make, the maximum variability that you have in the system is over the 1 in the bandits. but it is in general over the H in the nature as an MDP, because if you still assume that the rewards are bounded between 0 and 1, the value function can build up to the value of H during the full episode. So of course, this is, putting H there is nothing but an upper bound on the magnitude of the value function, more precisely on the range. What you would like to do is to use something more representative, that is more similar to the problem you are tackling. So you would like to put, for example, the maximum variability of the optimal value function. This should be it can be much smaller than H. And there is a line of research that is doing exactly this. They are constructing confidence interval assuming that you know the estimate of the bias vector. And one paper is actually appearing in this conference in ICML 2018. It is called SCAL. That paper is for the setting of infinite horizon MDP, and it is more challenging. What we do here is to try to construct something which can rely on the optimistic value function that we have available, and we correct it to maintain optimism. And we would like to show that the correction term that we make is really minor, and that the range of the value function that is optimistically computed is really converging to the true one. I guess the main idea is that the bandit MDP that we have defined is really not a worst case MDP, so it might be that we are able to do problem-dependent analysis for the specific problem that we have and prove better bounds. We said that the important part is the optimistic value function, and if we would like to understand what's the relation to the true value function, which is a property of the problem. And we do that in 2 steps. The first one is by looking at how the true value function is behaved. If it has, maybe it is nicely behaved, so it will hopefully points toward the right direction. And the idea is that the mistakes are essentially not very costly. If you make a mistake on the bandit MDP, you're going to lose some immediate reward, but then it's the same problem again. So you would expect the mistakes not to be long-lasting. And the second key part of technology is that the bandit MDP that we define is highly mixing, because it is a contextual bandit problem, and states are sampled from a distribution. And the optimistic value function, we can show it is converging to the true value function for this specific problem. And therefore, we are able to define concentration inequalities and an exploration bonus, precisely, that is shrinking if the problem is, in fact, a contextual bandit problem in the tabular setting. I guess we're going to take a first look at the optimal value function. And it's quite easy to show that it is limited in range. For example, if you think about starting from the best state, you can realize that you can get at most 1 unit of rewards if the rewards are bounded between 0 and 1, and then it's the same problem again. You're going to transition to a state which is sampled from a distribution. And likewise, if you start from the worst possible context, maybe the best action can only give you 0 reward, and then you are going to experience the same problem again. Using that, you can show that the range of the optimal value function is really less than 1, and therefore the interpretation is that you can make only mistakes that are non-long-lasting. You can only lose 1 unit of reward for every mistake that you make. It is not over the age. Next, we are going to look at the relation between the optimistic value function and the true value function. And we would like the random variable, which is the agent estimated value function, to converge to the true value function. Unfortunately, this is not happening in general. There was a nice discussion when the original UCRL2 paper came out from Peter Auer, and they were looking at how to bound the range of the value function. They did that with the diameter, and we do that with the time horizon in episodic MDP. And I guess really, the two are not converging in general, and this may lead to over-exploration. But luckily, on the bandit MDP, due to the highly mixing nature, we are allowed to show that the two are converging, and this is essentially due to the fact that the agent is forced to be visiting every state with a linear rate, essentially. So it has to learn what's the optimal policy there. And therefore, it has to obtain an accurate estimate of the value function. I'm not going to go through the main result because I think I am short on time, but you can find it on the paper. I guess the main conclusion is that we are able to transition between the two frameworks. The bandits are not identified via statistical test, and to me this is really surprising. It really means that there might be other frameworks that allow you to obtain a simplification of this type. In fact, you would be able to obtain these results as long as the range of the optimal value function it is bounded, and the MDP is highly mixing like ergodic. And we do this with a minimal modification of existing algorithms. And there are many others that actually already inherit this performance without the need of any modification. And I guess one question that we are going to leave for future research is, can we identify class of easy MDPs to learn? And can we design algorithms that automatically inherit better performance on this class of easy problems? Thank you. I'm not sure if I have time for a few questions. Yeah, we do. Thank you. Not really. Okay, thank you.
Is there any question? If that's the case, please use the microphone. In the meantime, so Sven is basically set up. Okay, so question from my side. So you mentioned earlier that with function approximation, we can't do reliable exploration. Can you kind of like explain what the intuition behind that is? What is the key problem there?
Oh, I guess we just need more time to figure out how to obtain provable guarantees, because there is a huge difference between theory and practice right now. Practice, people are using deep learning, and it is performing very well, but it is needing a lot of manual fine-tuning, and we would like to remove that. We would like to obtain something that is reliable. But unfortunately, to my knowledge, there are no results that provide polynomial bounds for exploration with value function approximation, even in the easy case of linear value function approximation. So basically, we don't have an algorithm to start from, and from there examine the reduction to contextual bandits, maybe with linear contextual bandits.
Okay,
thank you.
Thanks, Andrea, again. And our next speaker is Sven Schmidt, and he's talking about learning with abandonment.
Hello, everyone. Is the mic okay? Too loud? Okay. Sounds loud to me. Anyway, thanks for the organizers for inviting me. Very excited to talk about learning with abandonment, which is joint work with Ramesh Johari. So when we think about learning with abandonment, this is what we have in mind. So think about a platform that interacts with the user, and through that interaction is able to learn about the user's preferences over time. But there's a risk. The risk is that if the algorithm upsets the user, then this user will leave the platform, and that is something the platform wants to avoid. Now, I want to note that if this general idea is interesting to you, there's another work by folks from Colombia that attacked this problem from a very different flavor. But our setup is as follows. Or before I move in, let me talk about applications that will illustrate where this happens. So for example, think about newsletters. So a platform sends newsletters to its clients, and it might want to send more newsletters to more engaged clients than to others. But of course, it needs to learn whether how many emails a client wants to get. But the risk for every newsletter is that there's this unsubscribe button, and if the client clicks that button, they'll never get an email again, right? Originally, our motivation came from smart energy meters, where energy companies want to throttle your electricity use when it's expensive. Again, they have to learn for specific users what their tolerance is, or else they risk the user to cancel their plan. And finally, another application is smartphone notifications. So if a Twitter or an Instagram sends notifications to users, maybe they want to send more to more engaged users, but with every notification, there's again the risk that someone turns off their notifications. So keep these applications in mind for the problem we study. And so our simple model that we go over as a baseline looks as follows. So suppose the user has a threshold drawn from some distribution, and for now I'm going to assume that this distribution is known. And now the platform at every time selects an action, just a real valued number, say. And if this number is less than the user's threshold, the platform gets a reward, which is a function of the action. Think of this as increasing in general, and it has some mean function that depends on the action. So it receives this reward as long as the action is below the threshold, otherwise the process stops. Now, the goal of the platform is to find a policy that is a sequence of actions that maximizes the sum of discounted rewards up to the time that the process stops, right? So the objective looks complicated, but I think intuitively it's not that hard. So you just want to get as much rewards without crossing this threshold. And then there's this discount factor that is anything between 0 and 1. Okay, so for an example, simple example, suppose the threshold is drawn uniformly between 0 and 1. And the reward is just whatever action you take. So for example, suppose a platform takes an action of a half, then with a probability half, this will be below the threshold, and the platform gets the reward, and now the platform also knows that the threshold is between a half and 1. Right? So you'd think that this optimal policy probably looks increasing, but it turns out that's not the case. In this setup, the optimal policy is actually constant, and not just for this special case, but basically for any distribution and reward the distribution you can think of. And what you do is you basically maximize the instantaneous profit at the first time and then stick to that action. So you either get lucky and play that action forever, or the user leaves immediately. Now, we have a bunch more results on this single user setup. So for a single threshold, what I just talked about, the constant policy is optimal. Now, the other extreme you can think of is that at every time, a new threshold is sampled for this user. Now, obviously, then no learning is possible across time, because every time you get a new threshold. So again, an optimal policy is a constant policy. But it's interesting to ask what happens in the middle. So we analyze this model where there's a constant part and an independent part that changes across time. And what we can show is that if we're pretty close to the single threshold model, then a constant policy is approximately optimal. And note that here the errors do not need any independence assumption. They just need to be bounded between minus y and y. And then on the other hand, if it's very close to the independent threshold model, then the constant policy is also approximately optimal. In between, we know that the optimal policy is increasing, but also intractable. Now, for now, I've talked about this single user problem where we know the threshold distribution and the reward function is also known. Now, next question is, of course, suppose we don't know these, but instead we have a bunch of users one can learn from. What can we do in this case? And so here the setting is as follows. Users arrive sequentially, and we're going to consider constant policies per user, as we know that a constant policy is optimal. Note that here I consider the case where the threshold is drawn once for each user. I'll make the following mild assumptions. The first one is that the distribution over threshold is supported on 0, 1. And furthermore, this instantaneous profit function, that's the reward times the survival probability, is kind of concave. I think about it as concave. It's a little milder than that, but it's good enough. And then we're going to look at regret, which we just measure as, suppose if you know f and you know the reward function, then you know what the optimal action is. Suppose you play that at all times, then look at how that changes when you play, if you play your whatever algorithm you play over time. So we use the approach by Kleinberg and Layton, and what you do is you simply discretize the action space into k actions, and you can run UCB or KLUCB on this discretized actions, and then we can get a regret bound of square root n log n. I'm going to speed up a little bit. Then the final part of our work is about feedback, and here the idea is think about smartphone notifications. If you send a notification to a user, there's not just two actions. One is opening the application and interacting. The other one is turning off notifications altogether, what we consider abandonment. But the third action is that the user just ignores the notification. So we include this in our model by saying with some probability you just get no reward, but you get to continue. And with probability 1 minus p, if you cross the threshold, the user abandons. And then there's two interesting phenomena. The first is that of partial learning, where there's a phase where the optimal policy adapts to the user's preferences, but at some point it's going to play a constant policy. And the second interesting part that we empirically show is that if you have this constant policy, you can look at the first action of this optimal policy with this feedback mechanism, and you can see whether this action is larger or smaller than the constant policy, and we see that sometimes it's aggressive and sometimes it's conservative. So I know this went really fast, so if you're interested, come either talk to me at poster number 99 or shoot me an email if you're watching the World Cup. Thank you so much.
Are there questions? Can you please use the microphone? And you can set up.
Oh yeah, let him set up.
Hi. So I think in a real setting, probably a probability of a user disengaging will also depend on how much you interacted with them in the past. Mm-hmm. So do you have a way of generalizing your model to that situation?
Yeah, that's a great question. So that would be a great extension. The hard part is that if policies depend on the entire history, obviously they're going to be much more difficult to characterize. And so you very quickly turn into intractable problems. So that's the problem there. I think that's an interesting way to look at it. Note that this probability, you can think of it as a user just having a geometric probability, so that some users have kind of more patience than others. But I agree that it would be interesting to think about how to include more history, but it makes the problem very hard. Thanks. Get out of the way.
Any other question? Okay, then thanks, Sven, again. Our next speaker is Kavosh Asadi, and he's going to talk about Lipschitz continuity in model-based RL.
Excellent. Thank you, everyone, for joining the session. My name is Kavosh. I'm a PhD student at Brown. I'm going to present a joint work with Dipendra Mishra from Cornell and my advisor, Michael Lidman. All right, so in this paper, we are going to focus on the model-based approach to reinforcement learning. In the model-based approach, we typically start from a policy. We use the policy to act in the environment for a while, collect some experience. We use the experience then to learn a model, and then we use the model to plan and come up with a better policy. Now, specifically in the model learning step, typically what people do is to learn a model for one-step transition and reward dynamics of the system. This model, in general, could be inaccurate. And then what we typically do in the planning step is to perform multi-step predictions as follows. So we start with a state, we feed it into a model to predict the next state. Then we feed the next prediction to get the prediction after two time steps and so on. Now, if you carefully think about what's going on here, after one step, because there is some error in our model, we are not going to exactly match the real next state. But in the second time step, there are two kinds of errors. So the first one comes from the fact that the model is imperfect. But the second kind of error is that even the input of the model was wrong in the first place. So it is plausible to think that our estimate is very wrong in the second time step, and it's super wrong in the third time step. So this is a problem which is sometimes referred to as the compounding error phenomena. It observes when the model is imperfect, which is basically almost all the time. And this could be due to some estimation error in your model learning process. It could be due to partial observability, or simply that even if you had infinite amount of data, you cannot still represent your model accurately. So let's see an example of this in the popular game of Pac-Man. So on the left-hand side, I'm going to show you the output of the emulator. On the right-hand side, it's going to be the output of a model, a one-step model trained using mean squared error. So what we can see here is basically after a few time steps, the model is completely off the rail, Pac-Man is gone, and the ghosts are also gone. And so if you use this kind of model and this kind of multi-step predictions to plan, then you are not going to come up with a good policy. So this brings us to the main message of this paper, which is the following. Lipschitz continuity plays an important role in the problem I just described, which is the compounding error, but more generally in the theory of model-based reinforcement learning. So let's quickly explain what we mean by Lipschitz continuity. So imagine we have a function, f, we have a point in the domain of the function and the value of that function. If you give me the Lipschitz constant of the function, then I can bound the value of the function at any other point. Okay, and the slope of these red lines are given by the Lipschitz constant. Now, for completeness, here's the definition. So you compute this ratio, take supremum, and basically in the continuous case, this means the magnitude, the biggest magnitude of your derivative. Now, the second definition I need is a Wasserstein metric. And the reason we need this metric is we care about the stochastic settings. So Pac-Man as an example, we want to be able to say, well, what's the distortion or the difference between the distribution predicted by your model and the actual distribution? This could be a one-step prediction or, in general, n steps. So here is one way of thinking about Wasserstein. So imagine, let's think about these probability masses as a bunch of boxes you want to move around. And you want to move it around most efficiently. So you want to move this from surface mu1 to mu2. That's one way of doing it. You just move green 2 steps to the left. This gives you the average cost of 2/3. There are other ways. So for example, here is one. In this case, you also move red and blue, which turns out not to be a good idea. And here is the last one. In this case, because the best you could do is 2/3, that's actually your Wasserstein error. So for completeness, I also give you the mathematical definitions. The average cost under a joint, you can construct the joint, but you need to make sure it actually matches the marginals mu1 and mu2. All right, so the first theorem, it talks about multi-step prediction error. It says, imagine we have a one-step model that is accurate, that is delta accurate, where we quantify error using Wasserstein. And also imagine, and also assume we have a Lipschitz model, an actual Lipschitz model, and a learned Lipschitz model. So both are Lipschitz. Then what happens after n step? That is to say, what is going to be the error if we predict using the model for n steps compared to the actual real world? Turns out the error is going to be a function of one-step errors, but also the Lipschitz constant of your transition model. So this k is the minimum Lipschitz constant of the two, meaning the real model and the learned model. So you see a huge dependence on the Lipschitz constant. Now the second theorem says, I told you planning goes from a model to a value function. So if the model is poor, how bad could the value function be? We want to also answer that. So here by Vt, we mean the actual value function, and by Vt hat, we mean the value function computed using your model. Turns out that this is also related to your Lipschitz constant. So k is the same k as the previous slide, the minimum of the two k's, transition model. But also you have this kr term that comes into the equation just because we're talking about value functions. This is the Lipschitz of a rho bar signal. I should also mention these bounds are tight if we are talking about linear MDPs. So the last theorem is about the structure of value function itself. So we want to say under a generalized value iteration algorithm, we want to say if we have a Lipschitz reward signal, a Lipschitz transition model, and a Lipschitz operator, is it true that the Q function is going to also be Lipschitz? Interesting question to ask. And the answer is actually yes. And we can bound the Lipschitz constant of Q function, and the bound is, again, a function of the Lipschitz constant of reward and transition model. So to use this in practice, we want to be able to bound the Lipschitz constant of neural nets. For example, if we are going to approximate our transition models using neural nets, if we use ReLU activations, turns out it's a very simple problem because ReLU is Lipschitz 1, so is bias addition. So we need to only care about the weights multiplication, and given what kind of norm that you like to define your Lipschitz with, you will get different kinds of constraints, and in practice you need to just make sure whenever the weights go off the ball, the desired ball, you project them back. And this is easy to do. So I'm just going to list the contributions. I think I can go through them. So I showed that Lipschitz continuity plays a key role in the theory of model-based RL. I showed that Lipschitz constant, how we can quantify the Lipschitz constant with neural nets. There are experiments in the paper, and their main message is it is beneficial to control the Lipschitz constant of your transition models. We also provide a new expectation maximization algorithm to learn stochastic models. We argue in the paper why we study this setting using Wasserstein. There are a couple of reasons. And finally, we show an equivalence between Wasserstein and value-aware model learning, which is a recently proposed loss function in reinforcement learning. And with that, I'm happy to take questions. Thank you.
So again, please use the microphones for questions. Okay.
Question?
Okay, please use the microphone.
Howdy. It seems to me your method is restricted to models that give the distribution of the next state. And in that sense, I suspect you're also limited to basically a tabular state representation. And if not, then how can you talk about the distribution over the next state if you don't have a tabular representation? Thank you.
So both are not true, meaning Wasserstein, you can still define the error if you have an expected model. So the theory basically works. And in practice also, we talk about how to learn the stochastic models in continuous state spaces. So both the theory works and in practice we can learn these models.
So a quick follow-up then. You're iterating the model, taking the distribution out, expected distribution out, and you're sending it back in again.
So we are not, so that's for theory. In practice, you can imagine you just sample from the model. There's no like, let's input the distribution.
Okay, thank you.
Sure.
Okay, our next talk is by Will Dabney on implicit quantile networks for distributional reinforcement learning.
Thank you. This is joint work with Georg Ostrovsky, Dave Silver, and Remy Munoz. And all of the algorithms I'll be talking about are really based on DQN. So they share the replay buffer, target network, and a lot of other aspects that I won't be talking about. But let's revisit what DQN is doing. It's learning a mapping from states to estimated action values, and these are means over returns. And the return is a random variable. And in distributional reinforcement learning, what we're trying to do is we're trying to learn or model this full distribution of returns instead of collapsing it to a mean. Last year, we introduced the C51 algorithm, which really takes the simplest approach to this possible. It discretizes the space of returns into fixed locations, and then just learns to assign probabilities to all those fixed points. Nonetheless, its performance outstripped many of the recent improvements to DQN. I'm showing the improvement over DQN in the bottom right here, but there are limitations to it. Nonetheless, later, Matteo Hessel put out the Rainbow agent, which is kind of the state of the art right now in Atari. And what they did is they actually took all of those other improvements to DQN and showed that they combine orthogonally with C51, this distributional algorithm, and showed really amazing improvement on Atari. At the same time, we tried to refine the core distributional reinforcement learning algorithm by addressing some of the limitations of C51. And the main limitation that we tried to address was this fixed discrete grid of return values. So instead of learning these probabilities of fixed return values, we learn return values for fixed probabilities. We did this with quantile regression and discretized the probability space. Now, in this work, what we tried to do is address this last bit of discretization and approximation. And that led to implicit quantile networks, which again are being trained with quantile regression or a Huber quantile loss. But instead of discretizing the probabilities, we actually end up with something kind of interesting. It's a conditional generative model of return. It reparameterizes samples from some base distribution, which we usually take to be uniform, into samples from the actual return distribution using a quantile function that we learn with quantile regression. And the performance is quite significantly better than QRDQN and actually approaching that of Rainbow. So the story, I don't have time to go through all the details, but the story of going from DQN to IQN is kind of actually encapsulated on this slide in its entirety. We make a change to the network, but it's a fairly minimal change. And all of the algorithm changes are shown here. And it's a story of going from the mean of a distribution, a mean of the return, to samples from that return distribution. So you end up inducing these TD-errors by taking a sample from the current return distribution and a sample from the next state's return distribution. And this produces a TD error, and you minimize a quantile regression loss on that. And you just take as many or as few samples as you want, and this learns a distribution, an implicitly defined distribution over return. So as I said, there's this kind of question of how many samples can you take. And it turns out by changing this kind of hyperparameter, you can control a data efficiency versus computation trade-off. Obviously, the more samples you take, the more computationally expensive the algorithm becomes. And what I'm showing here is kind of a hyperparameter sweep looking at changing the number of samples in the current state return distribution and the number of samples in prime that you take from the next state's return distribution. On the left, we look at, this is over 6 Atari games, averaged human normalized score. And on the left, we're looking at early performance, averaged over the first 10 million frames. And on the right, we're looking at the last 10 million frames averaged over a training course of 200 million frames. And so what we're seeing here really on the left is data efficiency or the speed of the learning process. And on the right, we're seeing final performance. And there's 2 really interesting outcomes of this. First, on the left, we see that increasing the number of samples increases how quickly you learn and increases your efficiency early on. This is expected, I would say, but it's nice to know that you can trade off spending more compute to get faster learning early on in the process. Now, surprisingly, on the right, we see that after about 8 samples per distribution, you don't get that much more benefit from additional sampling. So for final performance, you can get away with only about 8 samples per distribution, and you get the majority of the final performance benefits. And then finally, a really surprising and nice result is that if we cut the number of samples down to a single sample per distribution, which is computationally about the same as DQN, we end up not falling back to DQN's performance like you might expect. We end up here still being 3 times the performance of DQN, even while only learning by a single sample at each batch update. So let's talk a little bit more about the full performance. Like I said, Rainbow combines C51, this distributional algorithm, with prioritized replay and multi-step returns, dueling, et cetera. And IQN is built based on QRDQN. And the first result we have is that IQN halves the performance gap between QRDQN and Rainbow on these Atari 57 benchmarks. This is without adding all the additional Rainbow components, and we would expect that adding them back in would further improve performance over Rainbow. Next, we looked at the human start condition, which is where you evaluate based on trajectories that started off from a human play. And this is a bit outside of your usual training regime. And here we see an interesting reversal of performance. Now IQN significantly outperforms Rainbow. And finally, we go back to the no-op starts condition, and we look at the hardest games in Atari, the ones where the algorithm is still below human level performance. And here, IQN outperforms Rainbow. What this tells us is that in the first two columns, the entire remaining gap between our algorithm and Rainbow is on the games where you're already superhuman. It's the games where you're already very, very good, and Rainbow is a bit better at eking out that last bit of performance. Thank you very much. Come see the poster tonight at number 3.
Thanks a lot. Are there questions? Yes, please.
Can you tell us actually how you compare the samples? Like you're going to sample from these two things, and then you're going to have two sets of samples, and then you're going to compare them somehow. How does that work?
Exactly right. So the two sets of samples are samples from two different distributions, and all pairwise differences are TD errors. And you can combine these TD errors just minimized with a quantile Huber loss. So for instance, you can view it as you sample a return from the current distribution, you sample your reward, your immediate reward for taking an action, you sample the next state as you would normally, and the only additional thing is you sample a return from that next state's return distribution. This gives you all the components of a TD error. And then we're going to minimize the Huber loss, essentially, the quantile Huber loss on that TD error.
So I'm going to try and predict all of the samples from the next time step from all of the samples at this time step.
It's more like one sample here is suffering a loss due to any given sample from the next state's distribution.
That's what I meant.
Exactly.
Yeah, that's kind of weird, but okay, thanks for explaining.
Come to the poster.
Hi, thanks for the fantastic talk. I was curious, in your approach, if I understand correctly, you're using the distribution learning to get a more sensitive loss. Now, if you're learning a distribution, it also seems very useful for exploration. So I was wondering whether you've tried to apply it in this setting.
Yes, and also no. So something that I cut out of this talk was the risk-sensitive policies that you can get. I'd love to talk about it at the poster, but yes, you should be able to use it for exploration, but at the same time, it's important to remember that typically when we think about exploration, we think about uncertainty, like parametric uncertainty, the type that you would do with like Bayesian approaches, and this is very much learning a different type. And so in a stochastic world, the distribution won't necessarily collapse, and so you might kind of be doomed to explore forever, which means if you only do this, it might not be the perfect thing for exploration.
Thank you.
Just quickly ask Rich.
Thanks for the talk. Seems like distribution light is a general idea that cuts across lots of things, maybe helps a lot. But if that's true, why don't we find a way of showing that in a really simple problem rather than a complicated problem with complicated competitors?
That's a great question. The answer, I think, is that probably the reason distributional RL is helping has most to do with feature learning. I think we've ruled out a lot of hypotheses along the way, and I guess active work is investigating exactly why the representations learned with distributional RL are better than just learned under the mean value.
Okay, if it's quick, we can take it, otherwise...
Super quick. Did you try incorporating implicit quantile networks with the sort of bells and whistles you get from Rainbow and like comparing that? Like, do you still see the same improvements, or did you just not have time?
Exactly. We didn't have time. I just started some experiments very recently, and very, very early runs do seem to improve over Rainbow, but it's something that takes quite a while to run, and the hyperprimers are not the same. Anyway, thank you.
Okay, thanks a lot. And the last talk in this session is by Mohammad Garamzadeh on more robust, doubly robust off-policy evaluation.
Hi, everybody. This is joint work with our former intern, Mehrdad Farajtabar from Georgia Tech, and my colleague Yin Lam Cho, and we are in the DeepMind office in Mountain View. We are not on TV yet, but so this is about off-policy evaluation. I start with some preliminaries. So C is the trajectory, a T-step trajectory, which is a state X, action A, reward R. And since in this talk I'm going to talk about contextual bandit and RL, if it's T is equal to 1, we are talking about contextual bandit. If it's more than 1, we are talking about RL. So for a trajectory C, the return of that trajectory is all the discounted sum of the rewards that we observe along that trajectory, which we show it with capital R. And then when we have a policy, its performance is considered as a scalar, which is the expectation of all these returns of the trajectories generated by that policy. Or the other way is the expectation over all the initial states of the value of that policy at that initial states. And you know, if T is large enough with respect to the discount factor, this T-step return is very close to the infinite horizon return. So in this talk, we assume that this T is large enough, and when we talk about the performance of a policy, we are talking about this T-step performance, which is very close to the infinite horizon performance. So what is off-policy evaluation problem? So you have a policy called pi-e, which is the evaluation policy. You are interested in knowing its performance, but your data has been generated by a different policy called behavior policy pi-b. So you want to use the trajectories that are independently sampled from the behavior policy pi-b to have a good estimate of the performance of pi-e. And the performance of, and this estimator, we call it rho hat pi e, and an estimator is considered to be good here if it has a low mean square error. And since mean square error is bias plus variance, so if you have an unbiased estimator, low MSE is equal to basically low variance. And this has a lot of application, especially in industry. It's very important that you have a bunch of data generated by a policy. You use that data, you learn a new policy, and you want to have an estimate of the performance of the new policy without deploying it. So you have to use the data generated by the behavior policy to have that estimate. Okay, so this is also some notation. The first, the absolute continuity assumption is very standard in importance sampling, basically saying that if you have an action that has 0 probability under the behavior, it should have 0 probability under the evaluation, just to make this ratio not to blow up, and importance sampling is sound. And then when we talk about importance sampling, we are talking about the ratio between the evaluation policy and the behavior policy. This ratio is just one ratio if we are talking about contextual bandit. If it's RL, then we have the product of the ratio along the trajectory. So this omega from T1 to T2 is the cumulative importance ratio from the time step T1 of the trajectory to time step T2. So it's a product of this. And then the second bullet basically says that if you're interested in the performance of policy pi e, but the data is from pi b, and then you do the change of measure, then you need to also update the expectation by adding this importance, this cumulative importance ratio to the objective function. This is just the correction. So there are the existing approaches to of policy evaluation. The first approach is the standard control approach. It's a direct method that you learn the reward function and then you use the estimated reward function to calculate the performance. So when I use Q here, this Q is the reward function if it's bandit. If it's RL, it's just the action value function. So now the question is, when you go and learn this model, what kind of loss function you should use? So if you don't know what is your evaluation policy, this is an ill-defined problem because you don't know your model should be accurate at which part of the environment. But if you know what is your evaluation policy or what is your distribution of the evaluation policies, then this problem becomes well-defined because then you weight your, let's say, square loss by the stationary distribution of the evaluation policy or something related to the distribution of the policies that you would like to evaluate. And then we later replace that expectation with the sample average approximation. And since the data is not coming from the evaluation policy, from the behavior policy, the importance, the cumulative importance ratio is also, those omegas are also added there. And then the target Q is unknown. We replace it with the Monte Carlo. And then this is going to be an unbiased estimate of the original objective function, and therefore the beta star n, the parameter that you estimate, almost surely converges to the beta star, which is the solution to the one. Just to see how this optimization problem looks like for the bandits problem with deterministic evaluation policy, this is the weighted least square problem that you need to solve. So the weight basically is very simple. It says at each state for the action suggested by evaluation policy, if this action has low probability under the behavior policy, this is a valuable sample and we need to weight it large. And this is exactly the weight that you get there. The second approach is importance sampling, which you all know. We add the importance ratio to the estimator, and if the absolute continuity assumption holds and the behavior policy is known, this is an unbiased estimator. And this is just the vanilla version of importance sampling. In practice, you can use the stepwise version, or if you don't care about unbiasedness, you can use the weighted version or weighted stepwise version and get less variance. In practice, people are using that. The other approach is the doubly robust estimation. This idea has been around in statistics since the 70s, but it was brought to our community first in the bandit literature by Dudik and colleagues, and then in RL by Jiang Li and Thomas and Brunskill. And this estimator is a combination of model learning and importance sampling. So you see the V hat and Q hat, which is the model learning, and you see the omegas, which is the importance sampling. And the nice property of this estimator, which the name doubly robust comes from, is the bias of the estimator is the product of the bias of the model and the bias of importance sampling. So it's an unbiased estimator is if either of these two is unbiased. Okay, so what is the idea of MRDR, or more robust, doubly robust, that we have here, is basically a variation of doubly robust in which the loss function that we use for learning the parameters of the model derived by minimizing the variance of the doubly robust estimator. So basically, this is an estimator that has the lowest variance in the family of doubly robust estimators. And also, it naturally gives you a loss function for the model. Just go back to that bandits with deterministic evaluation policy. You remember, this equation was the weighted least square that we were solving, and that red thing is the weight. If we use the MRDR loss function, that weight changes to this term. So this is basically the weighted least square problem coming from minimizing the variance. And so, as I said, this idea of more robust, doubly robust also were around in statistics, and people used it for regression when a subset of the samples missing their labels randomly. So the contribution of our work, and this is the work by Cow in 2009, the contribution of our work is bringing this idea from regression with missing labels to contextual bandit and RL, formulating the variance of the DR estimator such that the gradient of this variance with respect to the model parameters can be estimated from samples easily. Because if you look at the formulations from the previous papers, this delta, which is the bias, is appearing in the formula. And since Q is unknown, you cannot basically handle it well. So you need to come up with new formulas for the variance of the DR that when you take the derivative with respect to beta, you can estimate it efficiently. And if you do that, then you're going to have sample average approximation, which is going to be unbiased. And then we also show that it's going to end up a convex quadratic function of Q beta, which is a function of the model parameters. So it's basically nice to optimize. So in case that Q hat is smooth, you can easily and efficiently find the model parameters using a stochastic gradient descent. If it's actually linear, you have a closed form. If it's not, then you can use SGD to calculate the model. So we applied this and compared it with the direct model, importance sampling, and doubly robust, and some other estimators that is not on this slide, but is on in the paper and the post there, in 9 bandit problems from the original paper by Dudik and then the Microsoft people at Microsoft, in 2 different scenarios. The hard case when there is a big mismatch between the evaluation and the behavior policy on the right panel, and the easy case when the mismatch between behavior and evaluation is small, as well as 5 RL problems from the Thomas paper and his thesis, as well as the mountain car and the cart pole, which I think either both or one of them has been used in the Jiang and Li paper, in 2 different scenarios when the evaluation set is small, And this case, importance sampling has a very large variance and large MSE on the left, and the case that the evaluation size is big and the importance sampling is small. So thank you very much. If you have any question, you want to know more about it, and there are some challenges and important open questions that we have in the paper, and you want to know more and see more experiments, please come to our poster this evening at poster 62. Thank you.
Any questions? Yes, please.
Hi, Muhammad.
Hi.
Very nice paper, and especially the title. So is it true that you're basically throwing out the variance into this beta estimation, into this gradient estimation of beta? Or is it, so is there a trade-off between the reducing the variance in one point and then you have to play around with those two estimators?
So it's just the loss function that we use for beta is coming from minimizing the variance of the DR estimator. So it's going to be the minimum variance estimator in the doubly robust family.
Okay, so it's not like you have some other gradient estimation variance that you have to reduce for the gradient with respect to beta, right?
So then the question is, when you want to solve that loss function, if your model that you use is complex, then you need to do SGD. And, but if this is linear, you have a closed form. If it's a smooth, because of this convex form, you're going to converge very quickly. But if you're using neural network or complex structure, then you have to use SGD. And of course, we don't know which local minima you're going to converge to.
Yeah, thanks.
Okay, so please let's thank all the speakers of this session, and then I wish you a good lunch break.
Thanks, Mike.
Thank you. So.